Hello, my name is Ben Porter, and today I'm going to talk to you about 12-factor applications. So if you haven't heard of the 12-factor app, it is a set of rules and design principles that will make your app run a lot easier and be a lot more scalable and robust. They are, in my opinion, quite important, so it's very much worth learning the rules and following them. Before we discuss details about what 12-factor app rules are, I want to talk briefly about the history behind them, because I find that understanding the history behind things helps me to understand the decisions that they make a lot better. So the 12-factor app methodology came from Heroku. So if you're not familiar with Heroku, it's a really neat platform as a service that you can essentially get started with very, very easily, particularly if you're using a first-class language that is supported by them. So I got into Ruby on Rails quite a few years ago, and Heroku was the default. You almost didn't even consider anything else, at least as an individual who was creating an application. So Heroku made it extremely easy. You just follow their prescription, and your application just works. You can just push it up, and everything just works, and it'll be running in production and very scalable. So really, really neat. One of the important things that the 12-factor app methodology did is it said that in order for a platform like Heroku, which can feel like magic to a developer, in order for that to work, there are a set of rules and prescriptions that you need to follow in order to be compatible with it. So as the application developer, if you don't comply with these rules, then Heroku is going to have a bad time making your application run and scale. These are not unique to Heroku. So that's an important takeaway. It did start at Heroku, but these are principles that are universal. They are language and framework agnostic. So no matter what application language you're using, no matter what framework, the 12-factor app methodology is something you need to pay attention to and you should be following. We're going to talk about scalability in a slide or two here, but it is important to be horizontally scalable, and there's a lot of rules that you cannot break. Because if you do break them, then your application is no longer going to be horizontally scalable. So that's an important reason to pay attention to the 12-factor app methodology. So we've already kind of mentioned some of these reasons, but why care about 12-factor? Well, it will make and keep your application scalable. As long as you are following these rules, your application will scale, which is wonderful. The 12-factor methodology will enable modern agile workflows. So you've probably heard the terms CI and CD, continuous integration, and continuous delivery. Those are not just marketing buzzwords. Those are important things in the modern era of application development. And the basic idea there, if you haven't heard of these, is with continuous integration, every single change to the code base, typically a Git commit, is going to go through a set of test suites that will test the code itself and test how it interacts with other applications, that sort of thing. And it can also be deployed to test environments, that sort of thing. And it allows you to have a high degree of confidence that you're not breaking things with new code changes, which is wonderful, because historically, when we didn't have CI, we were in a state of constantly hoping things didn't break, and deployments became very infrequent because you were always worried about it. QA cycles became very long, and that just further compounded the issue by making deployments even harder, which made us want to do them even less frequently, and it's a vicious positive feedback loop. With continuous delivery and integration, we flip that. We say, because deployments are hard, we're going to do them more often. And that makes us address the pain points, which in turn makes them easier to deploy, which makes us deploy even more often, and that sort of thing. So we take that positive feedback loop and we channel it for good instead of evil. Another reason to care about 12-factor is portability between platforms. So if you've ever had to move an application from one platform to another, much like I have, as I explained in the beginning there, then you know that portability can be very difficult. If you are relying on particular implementations of things, then you can run into a bad time when you're trying to move to a different platform if things are done differently there. If you follow the 12-factor app methodology, then you become much more portable, because the majority of platforms will cater to this approach, particularly Kubernetes and OpenShift. Another nice thing about the 12-factor methodology is it sets a baseline expectation for others. So if you've ever had to work on an application with another developer or another team, then you know that everybody can kind of have their own way of doing things, and not everybody makes the same decisions, not everyone has the same level of experience. And with the 12-factor methodology, you can essentially benefit from lots of consistency. So others can expect that your code is going to be laid out in a certain way, and it's going to interact with the platform in certain ways as well, which can be beneficial. And that will make more sense as we get into the specific 12 factors here in just a bit. But the 12-factor app methodology also helps you to avoid common problems. You'd be amazed at how many applications and developers reinvent the wheel and rediscover hard lessons that have been learned many times. The 12-factor app methodology really helps to avoid that. If you can learn the 12-factor app rules, and especially the why behind them, which this video is intended to convey to you, then you'll be miles and miles ahead as you begin to create, design, and implement your own applications. Okay, we've mentioned that scaling is a really important thing, and that scaling is something the 12-factor app methodology can really help you with. So as we talk about scaling, we need to differentiate a little bit between scaling vertically and scaling horizontally, because the two are different, and they're different strategies, and they are done differently. So vertical scaling is typically the easiest thing to do, and it's the most intuitive for most developers. Scaling vertically is essentially taking the machine on which the application is running. So if you imagine this application is running on a single server, so one VPS, one physical computer somewhere, one machine. It's running on that, and it's handling traffic. Well, at some point, the traffic is going to get to the point where it's overwhelming the single machine that you're on. Maybe you have 4 gigs of RAM and 1 or 2 vCPUs, something like that, and you're running out of resources. So the natural thing to do is to scale vertically, which is essentially make the box bigger. So if you've got 4 gigs of RAM, then add some more. So give it 8. If you're using a virtual machine or VPS, for example, then this is typically trivial. It does require a reboot, so there will be a small amount of downtime in this case, but it's not difficult to do. If you're on a physical machine, then it is a little bit more difficult to do, but still very possible. So vertical scaling is obviously the easiest, and the application doesn't have to do anything, really, to make vertical scaling work. But the problem comes in, what happens when you have the biggest computer in the world? What happens when you're using the maximum VPS size that's offered by your provider? So now you can't go any higher. And it's also worth mentioning that with a lot of providers, the costs go up exponentially, not linearly. So you reach a certain threshold where you're paying more for less resources to make them bigger. So that's a good cost incentive right there. So the answer to this problem is horizontal scaling. With horizontal scaling, instead of making your single server bigger, you just add more servers to it. So if you've ever worked with a distributed application before, then if you haven't heard of this horizontal scaling before, then you're probably thinking, well, holy crap, how do I do that? My application, there's only one disk and the files are there. So, how do I have multiple copies of this thing running, and how does that work? Well, it does complicate things a bit, because now you're going to need to start looking at load balancers to start distributing the load between these instances, and you got to look at shared storage and things like that. So there are complicating factors that make scaling horizontally a lot more difficult. But it is the true answer to scalability. If you aren't able to scale horizontally, you will max out that instance size at some point. And then you're going to be in a real world of hurt, because you won't be able to go any bigger. So you need to be able to scale horizontally. And the 12-factor app methodology that we're about to talk about will make it so that you can. Okay, so if you've never been to 12factor.net before, most of this material comes from there. It's an excellent resource, and I highly recommend that you use it. These are the 12-factor rules that are listed on 12factor.net. And I've consolidated them here for an easy examination. We'll talk through them very briefly, one at a time here, and then we will dive into each one in more depth. So rule number 1, Codebase. One Codebase tracked in revision control with many deploys. Dependencies. Dependencies explicitly declared and isolated. Configuration is stored in the environment. Backing services are treated as attached resources. Build, release, and run. We're going to strictly separate build and run stages. The application will run as one or more stateless processes rather than threads, for example. Port binding. We're going to export services via port binding, not through other methods. Concurrency. We're going to scale out via adding processes, not by adding threads, because threads are local to a single instance. So think vertical versus horizontal. Disposability, we're going to maximize robustness with fast startup and graceful shutdown. Dev and prod parity, we're going to keep the development, staging, and production environments as similar as possible. With logs, we're going to treat logs as event streams. And with admin processes, we'll run those as one-off processes. Most of those may not make any sense to you at this point, but never fear, we're going to go into them in detail, as I mentioned. But some of these are more important, in my opinion, than others. So we'll spend more time on those that I believe are more important, but we will touch on all of them. So rule number 1, Codebase. So one Codebase tracked in revision control and many deploys. So these days, that revision control is almost always Git. Commonly, it's an implementation of Git called GitHub or GitLab, that sort of thing. There are many. But the main point is that you don't have separate code bases for different environments. So historically, it wasn't that uncommon to have, application-dev, application-prod, and these were two different code bases. And when you wanted to take some code from development and into production, you would move it over to that new repository. That is a bad practice. You want to keep them as close as possible. So one code base in revision control, but you deploy that code base out to different environments. So obviously you'll have a production environment where your users and customers actually access the application. You should also have a staging environment, which is as close to production as possible with the exception of the scale. So staging is typically a much smaller environment. It has a lot less data in the database, that sort of thing. But it should be as close to production as possible, meaning it runs on the same OS, on the same instance types, with the same database type. So if you're using a managed database, for example, in production, you would use that same managed database in staging. That way, staging is as close to production as possible, minus the scale, so that you can identify issues that will break production when they're in staging, rather than finding out in production, which is the worst place to find things that are broken. So with staging, the reason why the scale is typically different is because it's really expensive to run a staging environment as big as your production environment. If you have a small production environment, then maybe it's fine. But as you grow and scale, you may have hundreds or thousands of servers running in production, and that would just cost a fortune in staging, sometimes millions of dollars per year. Not many organizations can afford a staging environment like that, so that's why it's typically smaller. UAT, user acceptance testing, is a common environment, also known as QA sometimes. It depends on the organization and on your workflow, but that's a common environment. Developer 1, Developer 2, that sort of thing. Depending on how you're laid out, it may make sense for each developer to have their own deployed environment. This is particularly easy when you're on something like OpenShift, Kubernetes. You can have different environments for different developers, which is really nice. As a developer, it makes it a lot easier to try things and that sort of thing. Dependencies. So every application has dependencies. Even if you try to write most of the code yourself, you're going to have some dependencies. Rule 2 says that you must explicitly declare and isolate these dependencies. A 12-factor app never relies on implicit existence of system-wide packages. It declares all dependencies completely and exactly via a dependency declaration manifest. So if you're familiar with a lot of modern language tools, they often have package management tools, like Node has NPM, for example. Ruby has Ruby Gems. Elixir, which is something that I really enjoy, has Mix, and so on. Python has pip, for example. So there are typically packages in a package manager for the application language itself. But this goes even further too. This is where a Docker file can fit in, for example. With a Docker file and with containers, you're starting from some base image, which is explicitly declared somewhere. So at some point, there is a from scratch, and we build on top of it. With the Dockerfile approach for our application, we are going to start from some base image and add the things that we need. So we can add the operating system level packages in a container. And a beautiful thing about containers is that they can have different system level dependencies than other things running on the same host or the same node. We're getting close to the line of OpenShift there. Again, I'll refer you to the OpenShift discussion, but the point here is that all your dependencies should be explicitly declared. It is not good to rely on things that just pre-exist. So with a 12-factor application, we're going to have explicit dependencies. So rule number 3, config. So all config should be stored in the environment. When asking what is config versus code, it's sometimes a little bit murky, but most of the time pretty straightforward. It's going to be anything that would vary between deployments, between environments. So for example, if you would have something that's different in staging versus production versus development, then that would be configuration. That would be config. So the classic example is database credentials. Your production database should have a really strong username and password that restricts access, and also typically TLS certificates and things like that. In development, you probably don't care. Your password is probably password 10 or something similar. You may also have credentials to third-party services. So if you rely on external APIs, the examples here like S3 or Twitter, that sort of thing, then those would also differ between environments, because you don't typically want your staging environment or your development environments to actually send real email or make real tweets, that sort of thing. So those would be configuration examples. You'll also probably have per deployment values like canonical host names. So your production environment, for example, is probably going to run at www.example.com, whereas your staging might be staging.example.com or something like that. So host names is another example of something that would be in the configuration. So this config should be stored in the environment, and typically that means environment variables. There's a little bit more debate over whether config files are okay. If you come from the Java world where everybody freaking loves config files, then you probably are comfortable with that. If you come from a better stack, I tease, but if you come from a stack like Ruby or Elixir or Node, that sort of thing, then you're probably much more comfortable with environment variables. That is my preference. I try never to have config files. I try to always use environment variables, and that will keep you out of lots of trouble. So backing services. It is extremely rare to have an application that stands entirely alone. If you are developing a database, then you may not have any backing services. In fact, you probably won't. But unless you're developing a database, then you probably do have backing services. Even in this example here, we see Twitter and S3 as backing services. They also have backing services themselves in the form of databases. So the vast majority of applications you write are going to have some sort of backing services or attached resources. You need to treat these consistently. Basically, make no distinction between local and third-party services. For example, with the database, so in this slide, we've got a MySQL database that's running behind our production deployment. And we've got an outbound email service. You need to treat those as different. If you had a first-party backing resource that was, some other microservices, you need to treat that as well like a third-party service from the perspective of this application. Don't treat it as part of one giant distributed monolith. Otherwise, you will end up with a giant distributed monolith, which is not fun. This is mostly intuitive in a lot of ways. It's extremely common to be dependent on, say, MySQL. And most developers, even if they couldn't describe Rule 4 for you, they would still balk if you suggested, well, let's add some code directly to the MySQL code base, and let's add some application code to that and deploy it. and run that. Most would say, oh, no, that's not a good idea. Those are separate applications. There's so many benefits of modularization. Let's go ahead and not do that. So that is how you should treat all backing services per the 12-factor application rules. This is not always easy, and sometimes it's in fact very counterproductive. If you are a developer and you're building service A and service B, and service A is dependent on service B, it may be really tempting to try to blur the lines there, or have bidirectional dependencies, that sort of thing. But do not do it. It will make your life much easier, better, cleaner, more modular, and all the good stuff if you follow rule number 4. Rule number 5, strictly separate build and run stages. So if you've seen a modern CI/CD pipeline, such as GitLab, which is probably my favorite, GitHub offers this as well, and these are becoming kind of a commodity these days, so you can find them all over the place. But rule 5 is strictly separate these stages. So the build stage is different than the release stage, etc., etc. One of the effects of this is that it will be impossible to make changes to the code at runtime because there is no way to propagate those back to the build stage. So this is important for dependability and reliability. If you've had a web application that you've been in charge of that is at any level of scale or sophistication, then you understand the importance of knowing exactly what's running in production. If there's ever a question, is production code that's running, is that all committed to the original repository? If that's ever a question, then you're doing it wrong, and you're causing a significant amount of pain to yourself and to others. So keep these strictly separated. The ideal is to have a single build that results in some build artifact, most commonly an image, sometimes called a Docker image, although Docker is only one implementation of containers. But that build artifact should then be promoted. So nothing inside that image will change between staging and production. The only thing that will change is that configuration, which again lives in the environment. So that is outside of the code base. And the code itself may make decisions based on configuration that's passed into it, but those should never be hard-coded, and the code should never differ between, say, staging and production when it is promoted. Rule 6, processes. So rule 6 is to execute the application as one or more stateless processes. So if you have worked in an environment such as Java, then you've most likely used thread pools and threads. Same with quite a few other languages traditionally. You may be extremely comfortable with that model, and there are a lot of benefits. For example, with threads, you share the same memory space. So it's a lot easier to coordinate between two different threads that are running in the same process than with two different processes that are forced to use IPC mechanisms through the operating system, be it Unix sockets or TCP sockets, that sort of thing. But you are not going to be horizontally scalable if you don't do rule number 6, if you don't execute as one or more stateless processes, because a threaded application that is not able to function with more processes cannot exceed a single physical machine. You cannot share memory space from two different machines. Now, you Erlang people are probably thinking, well, actually, we've got some ways around that. Yeah, sure. Okay. I love Erlang and Elixir, so I'm going to let that one completely slide with no pushback whatsoever. But rule 6, these processes, this is really important. Some languages, you don't have a lot of choice. Like with both Ruby and Python, for example, you've got a GIL, a global interpreter lock. So you can't, in fact, do a ton with threads. So you do processes by default. But this is ultimately good. Now, I always get a question when I say this from a Java developer that says, so are you truly saying that I should have no threads in my application and I should just scale out with only processes? Well, when you get to a pragmatic point, especially in an application like in a framework like Java, where threads and thread pools can be super mature and super easy to use, I'm not saying that. You can use the threads, and that is okay. But what is critically important is that those threads treat themselves as stateless as possible and do not keep local state that is required. In other words, if you can add another process, if you can add another instance of the application and it will continue to run just fine because all the state is in the database where it should be, then that's okay. You can use the thread approach. But you will constantly run into this question of, well, should I add more processes or should I add more threads? So it's not going to be perfect, but there are trade-offs and downsides. It's certainly more efficient to have multiple threads than multiple processes because there's a lot of overhead involved in multiple processes. But anyway, this is something that you'll have to decide for yourself. But the rule says processes. That's how it should be done. It is important to drive home that these processes are stateless and share nothing. They should not keep local state. Any sort of state should be in the database or wherever it belongs. It should not be in the process. It should definitely not be in memory, and it should almost always never be on disk because that disk is most likely not shared among processes. So keep the state where it belongs in the database. Now, that doesn't mean that you can't cache anything locally or that you can't ever store anything in memory. It just means that if that entire process disappeared in an instant, the application would continue to run with other instances that were still there and still alive, and nothing would be lost. So a good example of that would be jobs server. If you have a job that runs for very long, then there's a good chance that it will have some state because you may be in the middle of processing some job. If that instance were to disappear, you can still maintain your statelessness and be in the clear from 12-factor app methodology if that job will be repeated. So if the job never completes properly, then your system will identify that, commonly used as with a queue, for example, and the job will be picked up again by some different process, by some healthy instance that is still out there processing. If that happens, then you are good. But if at any point the process that your application is running in could disappear and you would lose data or you would lose something, then you are not stateless, and that's something that needs to be examined. Now, there are some exceptions. It's okay to, for example, if you had a process just disappear into the ether, then you may drop that request. That one may become a 500 or a 502 or something from your load balancer, and that's okay. As long as the request can be repeated, and that would be fine. So hopefully you're using database transactions as well if you've got multiple things going on there. So in the event the transaction does not succeed, it will be automatically rolled back, that sort of thing. So those are things to consider with regards to rule number 6. Port binding. So export services via port binding. This is also really important. The 12-factor app is completely self-contained and does not rely on runtime injection of a web server into the execution environment to create a web-facing service. For example, a good old Tomcat, our friend from the Java world, that is not a 12-factor application approach. With the 12-factor approach, give them a container. Give them an image. That thing should start up. It should bind some port, some TCP or UDP port that is then the entry point for the service. So you can take this container and move it anywhere and start it up, and everything is self-contained, and it's always going to be through this port. It doesn't rely on some pre-existing Tomcat instance that's set up that will kind of inject everything into the execution environment, for example. So concurrency. So we're going to get a little bit of duplication here from some of the previous, like the process discussion. But again, this is so important when it comes to 12-factor apps. Scale out via the process model. In a 12-factor app, processes take strong cues from the Unix process model for running service daemons. So with this model, the developer can architect their app to handle diverse workloads by assigning each type of work to a process type. So the 12-factor app processes should never daemonize or write PID files, for example. And that also plays very nicely with containers. You don't want to be doing that kind of shenanigans inside of a container because you're fighting the system that way. So with concurrency, notice that we have different running processes. So this can be the same web application, the same exact code base, but just with different entry points, or even with just different labels. One entry point, but there's configuration that tells each instance you're a web instance, or you're a worker instance, or you're a clock instance, for example. So you can have this chart that varies quite a bit. So you can scale these things individually out via processes. So in this example on the right, we've got two web instances. So we've got web 1 and web 2, which is good because you always want to have at least 2 instances. I say 3 for high availability, and preferably in different availability zones if you have that luxury. And then you've also got 4 worker processes. So these can run on the same physical machine, or they can run on different machines. It doesn't really matter because processes are free of each other that way. They only communicate via sockets, which are a form of IPC, or inter-process communication. So you are good to go from a 12-factor app consideration. So we've got 4 different workers, 4 processes that are running, along with these 2 webs, and then this clock process. So your application should look something like this as well. You're basically always going to want a web tier and a worker tier, because the vast majority of applications will need to do some sort of processing that is best performed asynchronously. Either it takes a little bit more time or something like that. And so that's an ideal situation for workers to run. So when your application gets to the point where you need a worker tier, please keep this in mind. It is best to scale these out in processes, and it's very easy to just do this by having different entry points or different config. So rule 9, disposability. So you want to maximize robustness with fast startup and graceful shutdown. If you have worked on a Java enterprise application, you probably have died inside seeing how long it can freaking take to get going. I've moved applications to OpenShift that were written in Java that took 5 minutes or longer to initialize. That's insane, and it's so hard to scale quickly. But with disposability, the basic idea here is you're scaling out via processes, and these processes are disposable, so they can be started or stopped at a moment's notice. They can be destroyed and created rapidly, and this is an important aspect to scaling in response to demand, particularly if you have a spiky use case. Great example. I was working with a customer, and they were an e-commerce website. So they sold a lot of stuff through their website. They had a fairly static setup with virtual machines. They could scale, but it would commonly take 30 minutes or more for them to scale, and that's assuming that everyone was on hand to do it. It was not automated. Well, it was partially automated, but it wasn't fully automated, and it took some work. So one of the things that sold them on OpenShift is they had a year in which they had a Black Friday sale that went viral. They got orders of magnitude more traffic suddenly in bursts right around midnight on Black Friday. So lots of the IT people were good and hungover from Thanksgiving. They'd had lots of turkey with lots of good old serotonin in it, and they were tired. And then late in the middle of the night, all of a sudden the alarms start going off, and they could not scale anywhere near fast enough, and they lost an absolute truckload of money on this problem. So they decided to adopt OpenShift. So with OpenShift, scaling is obviously much better, but your app has to support that. OpenShift isn't some magic wand that comes in and makes your app scalable when it's not before. So disposability is an important piece of that. So at any point, these processes can be destroyed, and your application needs to survive. Your data must stay consistent. You should not experience any downtime, because there should be multiple other copies running at a time that can handle the traffic. And when scaling events happen, we essentially just throw more and more processes at it, and we put them in the load balancer so that traffic is distributed among them. If your application takes 10 minutes to start, it's tough to add new instances in response to bursty traffic loads. So you lose the ability to scale quickly and easily with that. Now, there are plenty worse things than a 5 to 10 minute startup time. You can still over-provision a little bit and be in the clear to handle some bursts and some spikes. But you definitely definitely need to be robust and graceful at shutting down. It's not okay to take 5 to 10 minutes to shut down, because sometimes shutdowns can be instant and immediate. You should begin to terminate gracefully when you receive a SIG term from the OS. And if you just disappear, like if you get a kill-9, if you get a SIG kill from the OS, then you're done. You don't have a chance to do any sort of cleanup on that process. So your application needs to be built in a way that you can have some other copy of it, some other process, pick up the load and continue moving forward without issue, or at least with no permanent issue. Again, it's okay to lose a request that was in flight or something, but your data should be consistent and not corrupted, and you shouldn't have inconsistencies there. So dev and prod parity. So with 12-factor apps, you want to keep development, staging, and production as similar as possible. We've already kind of talked about this, so I'm not going to hammer it to death here. But you do not want your development environment to be radically different than what's running in production. It's extremely common for developers to love Apple stuff, MacBooks especially. I work for Red Hat, so I'm obviously not one of those guys. Well, actually, that's not fair at all. There's a lot of Red Hat people that do like and use Apple products, but I'm not one of them. I'm one of those weird purists. So I've been suffering in agony for 15 years on the Linux side. I joke, I actually love it. No pain, no gain. But anyway, getting off track here. So it is not uncommon to have developers running on a MacBook, for example, and the first time their code runs in a Linux environment is in production. That is not good. At least, and even staging. It's not good if the first place it runs in Linux is staging. So, and it's not good enough to just do CI. A lot of people will think, well, my CI runs in a container, so it's running on Linux, so it should be good. Unless you have perfect test coverage, it's not good. It's not good enough, I should say. So the ideal is to keep dev and prod the exact same. Now, that can kind of suck, because what if you're running some crusty old version of RHEL in production? You don't want to run RHEL 6 on your laptop. That would suck. I totally agree. So there are ways around this, and containers are typically the answer in the modern day. If you develop locally inside of a container, then chances are much, much better that you'll be fine. Let me tell you a real-life story that has happened to me 4 different times. Developers on a MacBook where the file system is case insensitive. In other words, it doesn't care about a capital A versus a lowercase a. Those are the same character in a case insensitive thing. On Linux, that is not the case. The majority of Linux file systems, all of them as far as I know, but there could very well be some that I'm not aware of, are case sensitive. Capital A is not the same as lowercase a. This is a real problem, or can be a real problem, that comes to bite people. In a Mac OS development environment, particularly if you have a dynamic language that sources files at runtime based on their name on the file system, Ruby, excuse me, then it's very possible, and actually this happened once in a Rails app, but the other 3 times were in Node apps. So basically, everything works fine in development. And then you get into production and you try to start up the application and it can't find one of the source files. And you absolutely wreck your brain because you typically don't have SSH to production. So you're kind of just digging through logs, trying to figure out what in the world is going on. And this is not something that's reproducible in dev. That sucks. Having bugs that only exist in a deployed environment and can't be reproduced locally is a developer's nightmare. This is the sort of stuff that Rule 10 will prevent. If you are doing local development in the same OS, the same environment as production, then these sorts of surprises won't happen. Your code will never work in the first place if you have a case sensitivity issue, for example, because you're running locally you can be doing your development on a MacBook. But if you're running it in Docker, then you find this immediately, and it never gets committed, and it's 100 times easier to figure out what's broken when you just made the change, because it's very recent in your mind. So Rule 10, dev prod parity, is important. Continuous deployment, also known as continuous delivery, can really help to minimize these gaps. So if your Continuous delivery is basically taking a commit at a time and rolling it out to these different environments. Even if the bulk of your commits do not make it to production, if they at least make it to a QA environment or a deployed development environment or even staging, if they at least make it that far, then this really helps a lot at kind of combating the dev-prod parity issue. The time gap is super important. As I mentioned, if your code takes days, weeks, or months to go into production and your dev environment is not the same, imagine how hard it would be to find that freaking case sensitivity issue if the code was written months ago and it just bombed in production. Oh my gosh, I can't even imagine trying to debug that. That'd be horrible. So the time gap makes a big difference. That's also a reason to follow the continuous delivery model and deploy early and deploy often, because the time gap makes huge difference with developer productivity. The personnel gap, the developers write code, ops engineers deploy it. Hopefully, in a modern DevOps or a DevSecOps type environment, hopefully there's not a huge gap there between the people who write the code and the people who deploy it and monitor it, that sort of thing. It's ideal if developers do both. Now, in the real world, we know that DevOps skills and development skills have some overlap, but a lot that is not an overlap. So you very well may and probably do have DevOps people in your team, but minimizing this personnel gap is really useful. And having highly automated deploys where things are happening early and often, and you deploy frequently because it's very painless, then the same people who are writing the code are often the ones giving the okay to roll it out to production. So when things go wrong, the personnel gap is minimized. The tools gap. Developers can be using a different set of technologies in local development than they might in production. So this is becoming much more rare. It's been a long time since I saw an app that was using SQLite locally for developers while using Postgres or something in a production environment. And a lot of this is the gratitude of Docker Compose and containers, that sort of thing. It really wasn't that long ago that it was pretty common for a local developer to be developing on their MacBook, on their OS X, while using SQLite as the persistent storage for their app and using some sort of a development server. So they're not using a real reverse proxy like they do in production. So no Nginx, no HA proxy, that sort of thing. And the only thing that is essentially the same between dev and prod in that case is the Ruby code or Node or whatever. That is also not necessarily going to be true, because if you're using OS X for development, then you're going to have a situation where in the deployed environment, you have different tools, that are compiled differently and have different native extensions, that sort of thing. So there may be differences in the implementation. Keeping dev and prod as close as possible really can minimize this tools gap. So again, using tools like Docker Compose, you can easily have a Postgres instance that's the same exact version locally that you're using in production, and that is invaluable and definitely something you should do. So Rule 10 is important. So Rule 11, logs. So this is something that most developers don't really think about, but this is really important, especially when you're moving to new platforms, which again is something that I've helped to do many times. So a 12-factor app never concerns itself with routing or storage of its output stream. Basically, your process, your application should write everything to standard out. Don't write to a file. Don't try to do anything fancy. Just write it to standard out. It's not your application's job to handle those things. That is some other tool's job. It's the platform's job. It's the operations guy, whatever. It's not your application's job. So you should just write unbuffered to standard out, treat it as an event stream, and that's the end. Don't worry about it from there. So again, it's the Java devs that are probably like, oh man, no, dude, I've got my log file. I freaking love that thing. And that's the way it is. That's the way it works. Yeah, sometimes you don't have a lot of choice. As a Java engineer, you can advocate all you want for just writing to standard out, but you may not ultimately have the choice. So if that is the case, there are ways to fix this. The simplest and cleverest hack I saw was somebody just had a tail-f that would spawn inside of their container that would just tail the log file. So the application didn't have to change. It could just write to the log file all at once, but it would get rotated very aggressively. And the tail-f would spit everything out to standard out. So the platform, in this case OpenShift, was able to pick that up, and the fluentd that was part of OpenShift that was running on the node just vacuumed up that standard out and sent it to the Elasticsearch that was running on the infrastructure nodes for OpenShift, and the rest was history. So logs, treat them, just write it to standard out. Your application should not be writing to a log file. We're almost done. Last rule. So rule 12, admin processes. So run admin management tasks as one-off processes. This is one that I find to be surprisingly really confusing. And I think that maybe the reason I'm surprised is that as I mentioned, I got into Rails, Ruby Rails, quite a few years ago. So I learned the Rails way of kind of using these one-off processes to manage stuff. Admin management tasks. So it felt very natural to me. But at a basic level, Rule 12, what that is essentially is saying that one-time scripts, even if it only runs one time. So an example for this, a common one, is a data fix-up. So say that you're adding some column to the database, or some field, something like that. If it doesn't exist before, maybe you have to populate it with some sort of default data or copy it over from somewhere, whatever it is. This sort of thing happens all the time with web applications of any size. These scripts, according to Rule 12, should always be committed into the app's repo. These should not be something that you SCP up and you cowboy it into production at deploy time to make it work. That is bad practice, and you should not do that. And if you do that, it makes you a bad person. Okay, I'm joking about that, but you should not do that. All scripts should be committed to the app's repository. If you're touching the database, this is not part of 12-factor apps. This is just philosophy according to Ben, aka me. If you're changing or touching the database at all, even if it's not schema changes, even if it's just data fix-up changes, that should be a migration. Something that is tracked and has a proper system in place that runs. So the other part of Rule 12 is that these one-time scripts that you're writing, preferably, are not going to be completely reinvented stuff. There's a really good chance that your application already has functions and methods that provide access to the database. For example, when you're writing these one-time scripts, you should not be using pSQL and just have some raw SQL that does some stuff. Now, sometimes you may not have a lot of choice, but chances are you've already got some Java code or Ruby code or Node code or whatever that accesses these models. You should reuse that. That minimizes the surface area for bugs and for bad stuff to happen. So Rule 12 is to reuse the code and libraries that you already have for these one-time scripts and admin processes, and always make sure they are committed to the repo. I have the email address, freedomben@protonmail.com, and I am not fantastic at checking it, but do feel free to send me email there, and I will hopefully see it and get back to you. So thank you for watching. Much appreciate your time, and hopefully this has been useful to you, and all the best.